Welcome back to ECE 442-542. The passport assignment is past due. You can still turn it in if you haven't, but I think most of you have submitted a passport. That's your entry into the class, whether it's late or not. Homework, I won't be as forgiving. It's due on Friday, but I think you now have some experience with submitting work into the Dropbox based on the passport assignment. I have had several questions about homework number 1, which means you might want to at least look at it in the next day or two, hint, hint, so that you become a little bit more familiar. You don't want to be 11 p.m. on Friday the 30th trying to start homework number 1. You may be a little bit behind if you wait that long. We will be getting into Z transforms, and I've posted some reference material. We don't have a textbook, but there are many sources to that, and I've provided a section at the very beginning of unit number 2 in D2L. I hope everyone is starting to get comfortable with accessing the material on D2L. You should find some material there, and there might be others that you are more comfortable with. It really doesn't matter. You just need to learn the material prior to all of the exams, and our first exam is scheduled for, doesn't seem like, or it may seem a long way off, but 2 weeks from Wednesday we'll have our first exam. That's the 11th of February. I'm just trying to give you a heads up, meaning it won't catch you by surprise is the plan. Today we have a long list of topics that I would like to work through. The first is where we left off last time. Last time we talked about homogeneous linear difference equations. Let's now introduce a forcing term and see how that behaves or works. The next topic is really more, or should get you the information that you need to work problem number 4 on homework number 1. And we'll talk then about settling time for stable discrete time systems, and here's sort of a picture of what I'm meaning by that. Or settling time is really, it could be many different things in a discrete setting. One might be the number of samples it takes. It could also be the actual time interval in seconds that it takes. You need to be clear from the context what's being asked. Am I saying the settling time in a particular number of seconds, or am I referring to the number of sample periods? And those are just related by the sampling period, capital T, but it's really how long does it take to get within a tube that's 1% of the initial value. If we say, let's talk about the 1% settling time. Your response might get in that 1% tube very early, but we want it to get in there and stay in and be stuck in that 1% tube. If you have a signal that's oscillating, positive and negative, it might cross into that tube and then leave, then go through it again many, many times, but you want to think about what's the time when it first enters that tube and stays or remains in that 1% tube. That's what these dashed lines are supposed to be representing. Obviously, that's not 1% of this diagram in my initial condition, but it's hopefully illustrative of what we mean by a particular settling time. Problem number 4 on homework 1 maybe could have been reworded or stated more clearly based on some questions that I'm receiving. It's always clear to the writer. It made perfect sense to me when I worded it, but in terms of you understanding it, don't try to connect parts A and B's initial conditions and inputs. Those can be completely separate, parts A and B. And in particular, I think in part A, you're given no initial condition and some input value, and you're asked to just recursively find the response due to that applied input. Part B changes which maybe it's not that clear from the statement that it's changing, but there you don't have an input, an external input, you just have an initial condition. And I don't even tell you what that initial condition is. Just assume something that's non-zero. It really doesn't matter what it is. You can find the number of sample periods to get you within 1% of where you started. That's the idea on homework set number 1, problem 4, part B. Once we've worked through those, we'll get into some block diagrams in both the time domain and the frequency domain. Those are somewhat consistent with what you've already maybe seen relative to differential equations and S-domain or Laplace domain block diagrams. Here our blocks might be in terms of 1 over z, or z to the minus 1, which in the time domain that corresponds to a delay of 1 sample. In the time domain, we're looking at an all-delay block diagram versus an all-integrator block diagram that you might have had in a continuous time setting. Once we have block diagrams, we can do all sorts of things. We can find transfer functions, we can find state space representations, and we'll start to become more comfortable with that. Again, this is modeling. How do we get comfortable with these models or systems that exist in a discrete time setting so that we can go about controlling those or changing the behavior of those systems, since this is a digital control class. We will then talk about this z variable. How do we interpret it? I've already kind of told you one way of thinking about it. Z to the minus 1 is a delay of 1 sample in the frequency domain, but now we could have many different complex planes. You've hopefully become familiar with the S-domain complex plane, a real part and an imaginary part. You can have a similar plane for discrete time systems. It's now just the z-plane. But now interpreting what those points in the z-plane mean is different than what they meant in the S-domain. Where did you like to live if you had a system that had poles? I'm nervous, I guess, so I'm just going to walk around, get rid of some of this nervous energy, and make you feel like we're on, I don't know, some game show or something. I'll give you the microphone, maybe I'll ask you questions. If you're playing along at home, you don't get to see this, but you can just imagine somebody walking up and down the aisles and trying to interact with the crowd. Where was I? Different planes. That's why I was going up and down. The S-plane and the Z-plane. We'll figure out how to relate those and how the Z-plane locations correspond to particular time domain behavior. And that's this Z-plane to S-plane mapping or vice versa, and that will take us a long way in this class. If somebody now says, I want you to build me a low-pass filter, you say, okay, I can do that digitally. Well, maybe you're more comfortable with designing an analog low-pass filter, but we will learn ways to map those continuous time filters or those S-domain transfer functions into Z-domain transfer functions. Now that you have a Z-domain transfer function, you can realize that with a difference equation. If you wanted to, you could create a block diagram and then come up with a difference equation that relates the inputs and the outputs of that system. And now you can number crunch with your computer to do whatever filtering you want to do. You're going to have a lot of different options available to you. One question that you will always be needing to know is, how fast do we sample? What's this sample period, capital T? Or what's the sampling frequency? And that could be in many different units. It could be in hertz. It could be in radians per second. This is the way that you relate those quantities, omega sub s, f sub s, and capital T. And then if you're trying to sample a system, if you have a closed loop system that you're trying to control digitally, you now know how to relate its bandwidth to the sampling frequency that you might be using. And the rule of thumb, I keep holding up fingers and thumbs, but if you're at home, you might just hold up your thumb and say, oh, the rule of thumb is 30 times the closed loop bandwidth. That's this omega sub s. And then the line above tells you how to relate omega sub s to capital T, or F sub s. Wow. That was our roadmap for today. Did everyone purchase a vehicle that can go fairly quickly? Because we need to drive across this roadmap in the next few minutes. Okay, let's get started then with this difference equation that's actually now forced, or a non-homogeneous linear difference equation. And a lot of times it's easiest just to see it via an example. Let's say that we now have a difference equation that is relating x, that's our variable of interest, at time n to x one sample period before, and a weighted value of x two samples before. And let's now drive that with a signal that's 1/2 raised to the nth power. And this, let's say this equation is valid for all n, little n, that's our index, our time index. And I haven't told you what the sample period is, capital T. I don't even have to tell you for this system. I'm just going to sweep that under the rug, and we don't have to know what time absolute is evolving or happening between each of these sample periods or points in time. What's that right-hand side look like as a function of n, or time? And we're actually going to evaluate this for n bigger than or equal to 0. But now we have 1/2 to the 1. That's just, and 1/2 to the 0. We start at 1, we go down to 1/2, then we just start chopping that down. That's an exponential decay in discrete time. 1/2, 1/4, 1/8, it's shrinking, but you can sort of see this envelope of values that we're shaking the system with. We're kicking the system, but we're kicking it not with a step, but with something that decays exponentially with n. That's what 1/2 to the n on the right-hand side is doing. How did you solve differential equations? In your differential equations class, how did you solve a generic second-order differential equation? Do you remember? No, I don't. I forgot. You're not supposed to forget. You could solve it by breaking it up into pieces, couldn't you? You could say, let me look at what happens without a forcing term, the homogeneous solution. Let me look at the particular solution. Then if I add those together, I'm going to have my total solution. That's what we're going to do here, because we've already solved the homogeneous. This, if you remember, which you should, it hasn't even been a week since we've been in here together, but that's the same difference equation we looked at for the homogeneous linear difference equation, where on the right-hand side it was set equal to 0. The first thing you might do then is say, okay, let me examine the homogeneous solution. And what did we learn last time? What was the homogeneous solution? This is x sub h for homogeneous of n. We actually found a structure for that, didn't we? And we found the z's of our a z to the n generic structure. Our z's were, for these coefficients, -1 and -2. And our homogeneous was some scaling factor or coefficient a sub 1 -1 to the n plus a sub 2 -2 to the n. That really hasn't changed. That's exactly what we solved last time. So if you've forgotten, you can just go back and examine the notes from last time and say, oh, that's how he found, or that's how we worked through the homogeneous solution to that left-hand side equal to 0. Now, one of the steps that you need to be aware of now is once we have this forced or non-homogeneous, we don't want to yet solve for these unknown coefficients. This is slightly different. Now you leave them as variables and wait until you found the next step, which is the particular solution, and then you solve them for the unknown coefficients at that point. Let me just make that clear. Don't solve for a sub 1 and a sub 2 until we find the structure of the complete or total solution. Meaning we want to add the homogeneous to the particular, and then we can start looking for these coefficients a sub 1 and a sub 2 based on initial conditions or particular values. Let's now look at the particular solution. Again, going back to your vast knowledge of differential equations, how did you come up with a structure for the particular solution? Do you remember? What were you keying in on if somebody said, what's the particular solution to this differential equation? How did you force a differential equation? Do you remember some of the right-hand sides that you might have had? Were some of them sinusoids? Some of them were steps. Some of them were ramps. Some of them were exponentials. And what did you do? You said, oh, my particular solution needs to be the same type of structure as the forcing function. If that's the case, then that guides us into what our structure should be for the particular solution here. We can anticipate that our particular solution, x sub p of n, is now some unknown coefficient a sub 3, 1/2 to the n, where that 1/2 to the n is the same structure as what we're forcing it with. Now we do need to find that a sub 3 before we start combining the particular with the homogeneous. Finding a sub 3 now says, oh, just plug this structure in for x sub p. That needs to satisfy this governing difference equation. And x sub n we already wrote down. That should be a sub 3 1/2 to the n. Then we add 3 x sub n minus 1. Well, that's a sub 3 still, but now we have 1/2 to the n minus 1 plus 2 a sub 3, 1/2 to the n minus 2, equaling 1/2 to the n. That may look a little bit messy, but there's a common factor in all of those terms. The a sub 3, we want a non-trivial solution. We don't want to just set a sub 3 equal to 0, although that would satisfy. No, it wouldn't, would it? Not like the homogeneous. So now we're looking for a non-zero a sub 3, but common to all of those four terms is 1/2 to the n. We can cancel that out, and we're left then with the following relationship for that a sub 3 needs to satisfy. A sub 3 plus 3a sub 3, 1/2 to the minus 1, plus 2a sub 3, 1/2 to the minus 2, is equal to 1. Now we just have a sub 3 weighted by three different terms, which we can add up, and that's equal to 1. Those three different terms, 1/2 to the minus 1 is just 2. There's 6. We have 4 times 2, which is 8. So we have 1 plus 6 plus 8. That's 15, I hope, which says that we have 15a3 is equal to 1, or a sub 3 is 1 over 15. That's now what we needed in our particular solution. We had a sub 3, 1/2 to the n, and there is our particular solution. We can combine that with our homogeneous solution to obtain the complete solution. Or x of n is now a1 minus 1 to the n plus a sub 2 minus 2 to the n plus 1/15, 1/2 to the n. And we could now use our initial conditions to solve for a1 and a2. We might have two initial conditions. That would give us two equations and two unknowns. Our unknowns are a1 and a2. If you do that, if your algebra matches mine, which that may or may not be correct, but I ended up with x sub n equaling minus 2/3 minus 1 to the n plus 24 over 15 minus 2 to the n plus 1/15, 1/2 to the n, and that's now my total solution, or complete solution. Is it clear how that would be found if we don't spend time doing that? You now might have x at time 0 is given some value, x at time minus 1 might be given some value. You can now plug those values for little n into that expression. You have the value for x at those particular values of the time little n. The only unknowns are a1 and a2. You have two equations and two unknowns. You can solve those, and hopefully you get or obtain minus 2/3 and 24 over 15. What's this x of n going to do as n gets big, or as time increases? Any idea or clue? What's going to happen? Yes. You have two terms that are kind of ornery, don't you? You have one term that has -1 to the n, and if you just had that, you would just be oscillating back and forth, wouldn't you? As n evolved. Bang, 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 between the same value. But you not only have that, but you also have this -2, which is, where is that relative to the unit circle? It's outside, isn't it? It's big relative to the unit circle, and it's going to start growing, maybe not monotonically, it may be oscillating too, which it will be doing since it's a negative value. What's that third term doing? That one's well behaved. That's what we hit it with. We kicked it with something that's shrinking, but the natural behavior of the system is unstable. So once you kick it, it just goes crazy as n increases. Do you see that? And you could numerically evaluate that if I said, what is x at time 100? You could tell me from this expression rather quickly. You wouldn't have to go, okay, x of 0 is this, x of 1 is this. You don't need that because we found a closed form solution in this complete solution. Questions on that and how that relates to what we did last time, which was the homogeneous. This is fair game to solve. Maybe on the exam it will be a 12th order, maybe with two distinct forcing functions. Got to have some fun. But you now know how to address that. How many pieces would you have in your expression? What's the generic answer? It depends, right? Because some of those 12th orders might be complex, and those now might collapse down into exponentially damped sines and cosines, and we'll figure out what that looks like in discrete time systems as we move forward. Before we do that, though, let's move back into a domain that's better behaved. By that, I'm meaning a system that might be stable. That means that if you had this and that, you would want those to have an absolute value less than 1. And then you would have a stable response. Then these values for x would be decaying as n increases or collapsing. Let's look now at this question of settling time. For stable, that's the key word. Discrete time systems. And you can talk about all kinds of settling times. Maybe what we will try to focus on here, they're all similar. Let's just talk maybe and agree for this course that when I say settling time, that's the 1% settling time. Somebody, another course might say, no, I'm more concerned about the 5% settling time or the 2% settling time. But they're consistent, and the same approaches can be used for all of those. Let's just, whoa. That's not obeying my title, is it? That was kind of an unstable behavior. But it was bounded, so it was okay. It didn't go completely off my screen, did it? I didn't have to continually scroll to find the bottom. Just saying. All right, settling time, 1%. While my computer starts behaving, I'm going to give you a problem. And here, let's consider, for settling time, you can look at a particular system settling time. If you say, what's the natural system's behavior, then you're really not worrying about the forcing function. You just want to know, if I kick this system or initialize it at some non-zero value, how long will it take to decay down to 1% of where you started? Let's now consider an initial condition response. Which means our input is 0 for all n, and y of 0, the initial value for our variable, is not equal to 0. To make this maybe a little easier, suppose we have a first order, and then we now say y of n plus 1 is equal to a y of n, and let's say that a is 0.887. I want you now, in the next minute, I'll give you a minute to solve this. Tell me what the settling time is. How many sample periods is it going to take to settle to 1% of the initial value? Go. Is everyone settled on an answer? Have you reached a steady state value? Yes? No? Did you draw a picture? If you did, what would it look like? You're looking for partial credit on an exam, right? And so you go, shoot, I don't know exactly how to do this, but I do understand the idea. What's the idea behind this? What are you wanting to do? Is this system stable to begin with? Is it well behaved? Why is it stable? So A is a finite decimal value, but it's less than 1 is the more important issue. This could be a repeated decimal. It could be an infinitely long, it could be, you know, some multiple of the square root of 2. And as long as it was that multiple put it less than 1, we would still be stable. The key is the absolute value of a needs to be less than 1, and then we know that things are contracting. If you take a number, 0.9, square it, 0.81, cube it, 0.9 times 0.81, so now you're about 0.72. Keep going, it's shrinking, isn't it? Because you started less than 1. We have a stable response. It's well behaved. Now, if we wanted to think about what's happening, did anybody get thrown off because I didn't give you an initial value for y of 0? Did that cause you to stumble? And it could. You may get a little nervous. Wait, he didn't give me all the information. That's okay. You could just assume something, but let's just say there is y of 0. Maybe that's 5. Then what's going to happen? Well, we just saw that since it was less than 1, it's going to have this decaying behavior. I'm drawing these lines just to emphasize that we only know these values at distinct instants of, or at distinct sample periods. Let's say 1, 2, 3, 4. What we're looking for is we're saying, when do I get within 1% of y of 0? Or this is now 0.01 y of 0. And when do we get there and stay there? If this was going back and forth, we might be interested in our tube having a negative piece also, and then we're wanting to know, when does that oscillating behavior, this decaying, when does it get into that tube and never leave? And we're looking for the value of n. Maybe we call this, well, in this scenario, let's say that I'm too big here on my tube, but let's just say that one here is up a little bit. And do you see that if it was a continuous curve, you might have actually entered that tube somewhere between those last 2 points? Is that clear? But in discrete time, here we can say, well, 6 we're not yet there, 7 we're definitely there after 7 samples in this example. And this is not consistent with a equal to point whatever it was, 887, I think. Now, did some of you start just iterating and saying, oh, y of 1 is a times y of 0? You still didn't give me y of 0. Y of 2 is a y of 1, or that's a times a y of 0, or that's a squared y of 0. Y of 3 is a y of 2, which is a times a squared y of 0, which is a cubed y of 0. We're engineers. We see a pattern. What do you see? What's y of capital N? That's our key formula. That's the expression that we want. We want to find capital N, where y of capital N is what? If this is a 1% settling time, That's what we want, isn't it? We want y at capital N to be equal to or less than 0.01, 1% of where we started, and where we started was y at time 0. We now have an expression for y of capital N relative to y of 0, and that's going to be key. We can now say that y of capital N, which we want to be 0.01, so maybe I should have said that, y of capital N is now equal to 0.01 y of 0, which is a to the n y of 0. And this is why the initial condition didn't really matter. As long as it's non-zero, we can divide both sides through by that, which provides us now with a relationship between the left-hand side, 0.01, and a, and capital N. And what we want to do now is simply solve for capital N, where capital N represents the number of time steps or sample periods to settle to 1% of our initial value. And this is why we took algebra in school, so that we could solve these kinds of equations. This is screaming, maybe, we need to get that exponent somewhere other than in the exponent. And one way to do that is logs. If we take the logarithm of both sides, that exponent is going to jump down and be in front of the log. And 0.01, oh, that's screaming at us to use log base 10, since that's 1 over 100. And log base 10 is nice when we have powers of 10. Meaning, if we now take the log of both sides, and in particular base 10 log, since this is 10 to the minus 2, this allows us to say that minus 2 is equal to n log base 10 of a. And if a is a known constant, we can plug that in and solve for capital N. Capital N is minus 2 log base 10 of a. In our particular example, a was this 0.887 number. And how long is it going to take that system with a value of a of 0.887 to settle to 1% of where you started? We don't have a non-integer value of samples, do we? So that n equal to something that's 38.4 isn't quite right. The system transient will take approximately 38, and in fact it takes 39 sample periods. And if somebody knew what the sample period was, then you know in absolute time what the settling time is, or the system transient, how long it will behave or take. Let's say that's T sub s bar is now n times t. And I guess when I worked this some other time, I had a particular value of capital T. Maybe I don't need to say that just yet, or maybe I do. Suppose T was 440 milliseconds, 0.04. Then our settling time would have been 1.56 seconds in absolute time. That 0.04 just came out of the blue, but we'll derive something that's related to that in a little bit. This is the real time to settle. The number of sample periods was 39. The number, or the actual real time to sample, or to settle, was 39 times the sample period. Did anyone get that? A few. Everyone? Oh, the whole class? Why didn't you just stop me from deriving that? Was that okay? That's now a gift. You're welcome. That's problem 4B. Maybe. Okay, something like that. Will be homework 4, part B. Questions on that? That T sub S bar is different from when it actually may enter into the tube. It may be a little bit longer than when it physically might enter the tube if this was a continuous time system. That's why I put the bar over it. Let's now move into our next topic, which is that of block diagrams. And since we are dealing with difference equations, let's just do all delay block diagrams. Suppose we have a system W of n plus 3W of n minus 1 plus 2W of n minus 2 is equal to R of n. And when you're playing along at home or later tonight, you can vary that difference equation. You're going to get tired of this 3 and 2 and 1 for your coefficients. But it doesn't really matter. It hopefully is clear what we're doing. Let's now build an all delay block diagram associated with this difference equation. One way we could do that is we could solve for the highest indexed quantity of our dependent variable, W of n. Meaning, let's say W of n is now R of n minus 3W of n minus 1 minus 2W of n minus 2. And we want to now create an all delay block diagram that will essentially solve this linear difference equation. If somebody injected into this block diagram an expression for R of n and established the W's at the appropriate initial conditions, maybe it's initially relaxed, so there's no initial conditions, but R is something non-zero, then this block diagram will crunch through the values and be generating values, numerical values for W of n. Just like an all integrator block diagram might have done in a continuous time or differential setting. How many delay blocks do we need to build up this all delay block diagram for this difference equation? We only have 2 delays in this system, so now we need 2 delay elements. These are actually unit delays. And what I'm going to do now is I'm going to try to create that difference equation in this diagram. Meaning, let me make the output of this leftmost summing junction be the left-hand side of that difference equation. Then if I have W of n on the left and I process that or hold on to that for one delay, what's coming out of that delay block? And this is really difficult. It's just W delayed one sample, isn't it? W of n minus 1. If we do the same to the second, we now have W of n minus 2. We now have almost all of the variables present in our block diagram. We simply need to introduce this reference signal, or the externally applied system R of n, but we need to make that be all of the inputs coming into that summing junction. We want the outputs to be the left-hand side coming in. R of n is some independent expression. Then we take W of n minus 1, scale it by minus 3, add that in, and then take minus 2, use that to scale W of n minus 2, and that's now our block diagram. And if somebody wanted to, they could say, well, the right-hand side, let's say, is our output, and everything else is then the input and these internal variables, W. But that's now a block diagram, which sometimes maybe has a more intuitive feel than a difference equation. Now you sort of see how these variables are relating to one another in generating the output response. Suppose now somebody says, well, I want a state space representation associated with this green difference equation. We're almost there if we've already produced a block diagram. How did we generate a state space representation if somebody gave you an all integrator block diagram? Do you remember the strategy for that? If you'd taken an earlier class that dealt with block diagrams, do you remember how we built up state space representations? If these were now integrator blocks and not delay blocks, how did we build or generate a state space representation? What was going into the integrators were what we wanted to integrate so that the output of those integrators produced something related to a state space representation. What's in a state space representation? State variables, key, ding, ding, ding. We want to label the outputs of our integrator blocks as state variables. We do the same thing here. We want to label the outputs of these delay blocks as state variables. How many state variables are we going to have? 2. It was a second-order difference equation, wasn't it? Here it doesn't really matter. Let me say that this last rightmost delay block, let me call that x sub 1 of n. And let me call the output of this first delay block on the left another state variable, x sub 2 of n. There are my two states. And in a state space representation, I need to find equations for x sub 1 at time n plus 1. I need to find an equation for x sub 2 at time n plus 1. And I need to write those in terms of x sub 1 at n, x sub 2 of n, and the input at n, and nothing else. If I need an equation for x sub 1 of n plus 1, can I find that in the diagram? Are any of these signals in the diagram actually corresponding to x sub 1 at time n plus 1? Again, I just have unit delays, and the output of one of those unit delays is x sub 1 at the current time. Well, that must be a delayed version of x sub 1 one time step before. Meaning, x sub 1 of n on the right means that this signal right here is x sub 1 one time step before that. What about x sub 2 of n plus 1? That's going to be at this point, or at that signal. To obtain this state space representation, all I needed to do was define outputs of these delay blocks as state variables, which now allows me to write down equations for x sub 1 of n plus 1 and x sub 2 of n plus 1. And I need those to be functions of x sub 1 of n, x sub 2 of n, and r of n. Meaning I'm now looking for these coefficients. And that will be a state space representation of a second order system corresponding to that second order difference equation. Can I express x sub 1 of n plus 1 in terms of this linear combination of states at the present time n and input at the present time? What does x sub 1 of n plus 1 actually equal? From the block diagram, it's exactly the same thing as x sub 2 of n. And that's what we need. We need to write x sub 1 at time n plus 1 in terms of these other state variables, which means if I fill in these blanks, this becomes a 1, this is a 0, and that's a 0, and I didn't even have to put those in. X sub 1 at time n plus 1 is equal to x sub 2 at n. Is that clear? Where that came from? That's right there screaming at you in the block diagram as you designed it. What's x sub 2 of n plus 1 equal to? This one has a little bit more character to it. And again, you don't want to write anything in terms of n plus 1s on the right-hand side. You only want to write variables, state variables and inputs at the present time n. We have minus 3 x sub 2 of n. Minus 2 x sub 1 of n. And then 1 r of n. And that's just looking at what happens at that summing junction. The output of that summing junction is equal to these linear combination of state variables and inputs. I can now write this in a matrix form. Is it clear what these entries need to be? I have 0, 1, 0 for the top row, -2, -3, 1 for the bottom row of my system matrix. And for notational, I may call this system matrix. This capital Greek phi. The input matrix, sticking with the capital Greeks, this is a gamma. And did I define an output? I didn't, did I? Suppose that I call this y of n. I hadn't defined an output. Let me just say that that rightmost signal is the output, y of n. Now I can write an output equation. Y of n is some linear combination of states plus some linear combination of input. I have one output, so all of these matrices are one row tall, and I'm going to get off the Greek kick and just label this as H, and this is the output matrix, and the direct feed-through matrix is a capital J. What are the dimensions of that output matrix? It's one row by two columns. It's a 1 by 2 matrix. It has to be compatible with the state vector and the output. We defined y to just be x sub 1. If we make the output matrix 1, 0, that will just pull off x sub 1. And we didn't have a input directly coming in to force the output. So that direct feed-through matrix is 0. Can you tell me anything about the stability of this system? If you are playing along and remembering, that's the same difference equation we've been playing with all along. And what governed its dynamic behavior? -1 and -2. So those should be somewhere hiding in that state space representation. Yes? They are the eigenvalues of that one matrix. And that one matrix is the system matrix. And the system matrix is that capital phi. If we find the eigenvalues of that system matrix, that will give us the natural behavior of our system. Notice the eigenvalues of the system matrix phi actually equal -1 and -2, which were the roots of the characteristic equation that we found when we were solving that homogeneous difference equation. if we looked at it from this state space representation, the eigenvalues of a matrix can be found by looking at the determinant. That's what these vertical lines mean. The determinant of lambda I minus phi. In our case, we know what phi is. I is an identity matrix that has to be compatible with that phi matrix. Phi was 2 by 2, it was square. The identity matrix, that capital I, is a square matrix that's diagonal with ones on the diagonal, and it's 2 by 2. So that we now have lambda I minus phi, or the determinant of that, is now the determinant of lambda times the identity matrix minus phi or this is now the determinant of lambda minus 1, 0, whoops, 2, lambda plus 3. And for a 2 by 2, we take the product of the diagonals minus the product of the off diagonals. That's our characteristic equation. We have now lambda squared plus 3 lambda plus 2 equaling 0, or that factors into this lambda plus 1 factor, lambda plus 2 factor. And that's now we've come full circle, and now we've looked at the natural behavior of this system in a state space representation and found that it's the same as the linear difference equation. It better be consistent with what we found solving this in the time domain. Again, this is a time domain representation, this state space representation, but now it's written a little bit differently. Now it's in the form of this matrix set of equations. But that's the same system as this block diagram, which is the same system as that green equation. And you need to start becoming comfortable with the green equation, the block diagram, and the state space representation. The state space representation you can now almost visualize as being that. It's now just an interconnected block diagram with these blocks being delays and having particular weighting coefficients and summing junctions. Now, this is in the time domain. We also want to be playing or becoming comfortable in the frequency domain. And just like it's not too hard to transition a all integrator block diagram into a frequency domain block diagram, the same process or a similar process can be followed for transitioning from an all delay block diagram into a frequency domain block diagram. And what we will do is we will replace the delays with its operator in the frequency domain, which is z to the minus 1. this is a time domain concept, these delays, and this z is a complex frequency variable. Let's just do that, maybe without fully appreciating what z is, but let's just now show that we can build up this block diagram. Now we have, instead of delay blocks, we have z to the minus 1 blocks. Everything else is the same. All of our weighting coefficients, our summing junction is in the same place. It's just now we have magically gone into the frequency domain so that we don't have a little r of n, we have a capital R of z. But everything else structurally looks consistent. And this will actually help you maybe solve one of your other homework problems. Let's now find a transfer function. Let's call this output y of z. And let's do some algebra, but now this algebra is based on the block diagram, so I will just call that block diagram algebra. And the sort of the strategy here, I wouldn't call it a trick, but the strategy is to focus on the outputs of the summing junctions and write equations in terms of those variables. And I'm just going to call that E because a lot of times that's a generalized error signal maybe, or some kind of, so it's just convention to maybe have that be E. I can now say that E of Z is equal to all of the inputs going into that summing junction. One of those inputs is just R, capital R of Z. The other one, let's say if I am going counterclockwise and I go all the way to the far right counterclockwise, the next one is minus 3 z to the minus 1 E of Z. Does everybody see where that came from? That was simply this signal, which is that. The next one I'm going to do in a couple of stages. I'm going to say that the next one, the middle input into that summing junction is minus 2 y of z. Typically, you want to write these in terms of just two variables, maybe e's and r's, but I can replace y as a function of e. Y is just z minus 1 times z minus 1 e of z. And that will allow me to get rid of this y. And that now allows me to write e of z as r of z minus 3z to the minus 1 e of z minus 2z to the minus 2 e of z. And I can now combine my terms with e's and r's. I have 1 plus 3z to the minus 1 plus 2z to the minus 2 e of z is equal to r of z. And I now have an expression for e of z in terms of delay blocks. That's 1 over 1 plus 3z to the minus 1 plus 2z to the minus 2 r of z. That's a transfer function between r and e. If I wanted the transfer function between r and y, I know y is just z to the minus 2 times e. Or it's now z to the minus 2, 1 plus 3z to the minus 1 plus 2z to the minus 2 r of z. And now I have a transfer function, and maybe you don't like it in terms of z to the minus 1s or z to the minus 2s. I can factor that out. A common z to the minus 2. If you bear with me here, I'll be finished shortly. Now I have 1 upstairs. I have z squared plus 3z plus 2 downstairs. Those go away. That's just 1. And now I have this transfer function, g of z, between the reference input r and the output that I defined, y, all by block diagram algebra. And you can do that for one of your other homework problems, is the idea. And we'll figure out where we pick up from this on Wednesday. Thank you for staying a little bit after.